see which one the best one is. So, quiz questions, huh? What do you got? Didn't we do that? No, there's no rate. There's conduction. What? Oh, radiating power, yeah. How about in the problems here? What do we got? 11. Okay. Mr. James Jewell. Sounds like a good honeymoon. Okay. Oh, yes, we did. Yes, 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 yes. Because I showed you that original weight that goes down to stir the water to heat it. So if this water is going to fall from a waterfall, what type of energy are we talking there? Potential energy. That potential energy is going to go into heat. And potential energy is mgh, and the amount of heat is going to be mc delta T. We'll cancel out the m's. Now, what units do we always do this in? Potential energy is always in joules. So make sure then we are going to do everything in joules, and 1 joule of energy is kilograms times meters squared over seconds squared. We got to have everything in kilograms. Is that right? I'm brain farting. Yeah, this is meters. This would be meters squared. Yes. Kilograms times meters squared. Yes. Should be. Look at the difference. I mean, not much. No, I think when she splatters on the bottom and then creates more of this turbulent friction at the bottom, I think is what would do it. So we need to make sure then that we use this in this is in meters per second squared. This is in meters. We're looking for our temperature change. Since this is kilograms in our joules, we need to use a specific heat that is joules per kilogram for water. And joules per kilogram degrees Celsius for water, that value should be 4186 joules per kilogram degrees Celsius. That'll just fall out then. Yeah, that'll fall. It's just a matter of units then. All right, what else do we have on this baby? Yep. 4186 is in our chart here. It's joules. Right there. Liquid water, 4186 joules per kilogram. I'm on 14.1 on the back side of the first page. Back side of the first PowerPoint slide. Yeah, these specific heat values. Yeah, right here. Yeah, 4186. In joules per kilogram, right? All right, what else do we have on this baby? Do you know how to do 12? Yes. Okay, well, 2,000 kilowatts, how many watts is that? How many watts? 2,000 watts, right? And what is the unit for a watt? If you broke it down one down less, what is a watt? Say, so power is equal to work divided by time. Work is in joules and time is in seconds. So a watt is a joule per second. So the way to look at this then is you have 200 joules per second. So if you have 200 joules per second and you know how many joules for this, we can get seconds. Calculate then how many joules. This will come out to be joules. This is joules per second. Then you'll be able to solve that for time in seconds, and you'll have to convert to hours. Now, 200 liters of water. 200 liters, that's 200 kilograms, or 200 kilograms of water. Oops. What else do we have? Well, I'll outline it. I don't know what the answer is, to tell you the truth at this point. How much heat needs to be removed from 100 grams of 85-degree water to make ice at -5? So this is that chart. The chart we did that looked like this. So where are we at on the chart? We're about right here on this chart at 85 degrees. So remember that chart we looked at, we said, oh crap, I should have put it below the 0 line here, but this is my -5 right there when I'm starting on that line. I didn't start it. So this is cooling down the ice. This is melting the ice at the same temperature. And this was getting 0-degree ice up to 100, right? This line. So the first thing you need to do is you need to get your water from 85 to 0, right? So you're going to have to do Q is equal to MC delta T on that. All right, so that is to get water from 85 to 0. Then you need to freeze it. Then you're going to have Q is equal to M times the enthalpy of fusion. All right? Well, you still have to do that in the last step. So this is going to be Q is equal to MC delta T, and this is going to get you ice at 0 to -5. Yeah, so there's going to be 3 of them there to calculate. So if you didn't do the freezing, yeah, it's probably not that one. Yeah, what else we have? Anything else on this? Yeah, you can figure that one out. I'll let you Google that or something. What else? Anything on the problems? Eight. What do you got for 8? What is the resulting temperature change? So in 8, what do we got? We got Q is equal to MC delta T. Yep, we're bubbling this pig tomorrow. Yep, we're bubbling this tomorrow. So, what do we got here? This would be 40,000 calories, 2,000 grams, and the specific heat would be 1 calorie per gram degrees Celsius. I converted. You could have left this in kilocalories, and you could have left it in kilograms. It's going to result in the same thing. What is the resulting temperature change? You're just solving this for the temperature change, right? Yeah. Anything else on this baby? Okay, so we're bubbling this tomorrow. Let's talk homework. Homework, homework, homework. Homework, homework, homework. If we don't have any questions on homework, we can go on to the new stuff. All right, we're good to go. All right, so everybody have this sheet right here. We're going to do this. If you don't have one of these, grab one of these. Justin, you got one of these babies? Jake, you got one of these? Okay, so we're going to pull heat. We're going to get rid of heat. Now, since the next unit is harmonic motion, wave, sound, all that stuff, this is what I developed quite a while ago to introduce it. So, and I did this on graph paper. I just keep photocopying it. It's just a good it just works pretty well. So if 2 blocks is 1 centimeter, then obviously 1 block would be half a centimeter, right? So I have 1, 2, 3, 4, 5 waves. It looks like I messed up. Well, I didn't mess up. Let's talk about this then. How do waves B through E compare to A? And if we answer 2, 3, 4, 5, 6, then we can compare. So let's identify some of this stuff on the wave. The height of this wave here is our amplitude, A. So this is our amplitude, A. I'll put an A here too. Now, amplitude. If you want to have more amplitude on your stereo system, all you got to do is turn up the sound, right? That's all you're doing when you do that. So we get all done, we'll talk about sound. So how does the amplitude of B, well, what is the value? What is the amplitude of A in centimeters? This is 1 centimeter, isn't it? What's the amplitude of B? This would be 2 centimeters. 1 block is a half a centimeter, so half, 1, 1.5, 2. The amplitude of C is 1 centimeter. And the amplitude of D is 0.5, right? And the amplitude of E is 1.5, right? A half, 1, 1.5. So there's our amplitude. Now, in 3, what's our wavelengths for all waves? Now, wavelength, you can measure wavelength anywhere along the wave, because the definition from where you start your consideration of the wave until it starts to repeat where you started. Sounds kind of strange, but I could say, all right, I'm going to start my measurement here, and if I trace my wave out, it goes down, it comes up, and oh, once I come over this crest, I'm starting to repeat what I started, correct? So you could do your wavelength from, we would call this crest to crest, or you could say, well, I'm going to go down here, I'm going to trace out my wave until I get to, oh, now I'm starting to repeat myself on the bottom, so you could go trough to trough. Or most people, they say, well, I'm going to start right here. When I go like this, oh, I'm coming through this axis right here as a wavelength, right? So what I'd like you to do, let's do this. Let's draw a different colored dashed line. Since this is, A is one wavelength, and we'll come back up and label that. We'll draw a dashed line here. I just went all the way down with it. So here, wavelength is an upside down backwards Y. Would that be the correct? Or is it just an upside down Y? I call it an upside down backwards Y. Lambda symbol. This is one wavelength. So, what is my wavelength for wave A? My wavelength for A is 4 centimeters. Okay. And you can actually see in the drawing that I did, the wavelength in B is the same, isn't it? Okay, so we know the wavelength of B is 4 centimeters. And I'll just put the symbol for wavelength in here like this. The wavelength for C. So if we go here to here for a wavelength, 2 centimeters, 0.51, 1.52. For D, the wavelength is, yeah, we go all the way here. It's 16 boxes to get to here. And for E, let's fix this up. I want to make this go to my line, so we need to, I'll change to black. We need to go right there and go right there. So we should be coming through, looping like that, coming through like this. If we finished off E, so that it goes to the red, it would look like that. Now, what's my wavelength here? 1 centimeter, right? It's 2 blocks. My wavelength here is 2 blocks, right? When I get to here. So 1 centimeter. Now, if it takes 1 second to go 1 block in the x-axis, what is the period? The period, capital T. Otherwise, capital T before could also be what? Temperature. Time's going to be little t, but you'll know. Big T. Now, big T is the amount of seconds per wave. How many seconds per one wave? We don't put the 1 in. But the period is how many seconds for a wave? So if it takes 1 second to go a block along this x-axis, if we say this is there, the train of waves here, we would have 1, 2, 3, 4, 5, 6, 7, 8 seconds. 8 seconds to go 1 wavelength, so 8 seconds per wave. So 8 seconds for a wave. B has 8 seconds again, correct? How many seconds in C? 4 seconds, right? D, how many boxes along the x-axis in D? 8 to here, 8 to here, 16? Okay, so 16 seconds. And for E, two seconds, right? Now, what is the frequency of each wave? Well, your frequency is equal to 1 over the period. And if you do 1 over the period, these units are going to just flip. So for frequency per second, how many waves are in a second of time? So we can simply do 1 over my time up above, 1/8 of a second. But let's talk about the unit. It's waves per second. The unit of frequency is in hertz. So hertz is 1 over seconds. They don't do the way, typically you'll see it like this. You'll see s to the minus 1. This comes from the math identity that x to the minus 1 equals 1 over x to the positive 1. So seconds to the minus 1 is the same as 1 over seconds. It's an easy way to do, then you don't have to do a fraction. But hertz is 1 over seconds. It's waves per second, or simply s to the minus 1. So I'll put it in that way. If we take 1 divided by an 8, we are going to have 0.0125 hertz. Then we are going to have 0.0125 hertz again. 1/4 here. 0.25 hertz. 1 over 16 here. 1 over 16. 0.0625 hertz. And E is 1 over 2.5. I don't know why I did 3 decimal places. Yes, sir. It's a 1 over 16 should be another half of this. Yeah. Yeah. That should be 0.00625, right? No? Oh. Oh, cool. Ah, man. So 0. Good catch. Good catch. Yeah, what the heck? Man, I need the zeros in here. Okay. 0.125, 0.125, 0.0625, yeah. Now, what is the velocity of each wave? What units do we need for velocity? We need meters per second. So that means we can do the wavelength of the wave divided by our period in seconds. That would get us centimeters per second. The wavelength times frequency, because frequency puts the seconds in the denominator, correct? So your velocity you can do either way. Wavelength times the frequency would be meters per second, and velocity would be wavelength divided by the period. Either one. Now, what's the speed of each wave? What's our velocity of each wave come out to be? What's the velocity? 0.5, right? Centimeters per second? Is that right? 0.5, correct? Point 0.5 centimeters per second? They all should be 0.5 centimeters per second. Because this is what happens. You're not going to change the velocity, typically, unless you change mediums. Like sound will travel faster through the metal railroad tracks, which is why listening to the metal railroad tracks, you might be able to hear the train coming. It travels faster through steel than it does through air. Now we know sound won't travel at all unless there's air or something, some medium. We'll talk about that. I don't want to get. Let's go back up and compare now. So if we compare this, notice that we've changed the amplitude, we've changed the frequency, right? But what we've not changed is the speed. So how does A compare to B? What's the difference between A and B? There's only one difference. The amplitude is doubled. So we have twice the amplitude, and wavelength equals wavelength, right? And period equals period. The rest is the same. What about in C now? What do we change in C? Compare. Okay. The amplitude's the same, correct? Okay, the amplitude is the same. So when we did wavelength, it is, A has a wavelength of what the heck? Yeah, in C, yes. 4 versus 2, it's half the wavelength. And then we're looking at A and C. It is, C is half the period, right? And it is then double the frequency. Now let's just look at that. Let's talk about this. You definitely see that if this is one wave and this is 2 waves, it's half the wavelength. It is going to take the same amount of time to get to my red line. If it takes the same amount of time, I have more waves. In fact, I have twice the amount of waves per second. My frequency is doubled. If my frequency is doubled, that's half my period. The reciprocals of each other. So I should also point that out. If my frequency is 1 over my period, then my period is equal to 1 over the frequencies. They're reciprocals of each other. Now, what do we got for D? For D, we have half the amplitude, right? We have 1/2 the amplitude. Then we have double the wavelength. We have double the wavelength. Then we have double the period. We have double the period. And finally we have now again, if frequency, you can look at frequency as how many waves do you get till you get to this line. This is one wave. Let's say this line right here just takes 1 second to my line here. This would be 1 wave per second, 1 wave per second, 2 waves per second, a half a wave, right? Well, since we're on that, how many waves here? 1, 2, 3, 4, right? This has more wave. This is a higher frequency. If you get a higher frequency, what happens to my wavelength? It's less. Okay? So in E, my amplitude, what about my amplitude? It's 1.5 my amplitude. Wavelength is 1/4 my wavelength. My period is 1/4. And my frequency then is 4 times. Now, U what did I do in D has a longer wavelength, right? But it has a smaller frequency. This has a smaller wavelength but a larger frequency. Every time I make that statement, I'm talking reciprocals. One goes up and one goes down. We could look at that this way. This is what I usually, and I think I've got this somewhere. Let's say let's pretend that if I do a table like this, don't write this down. I think I've got it somewhere. Let's say my velocity is 24. It's not going to change. My velocity of my wave is 24. My wavelength is 2. What's my frequency got to be? 12, right? Well, what happens if I change my wavelength? If my wavelength goes up to 8, what's my frequency have to go down to? 3, right? Let's say my wavelength goes down to 1. What's my frequency got to go up to? 24. They act opposite of each other. That is the only way to maintain the same speed of our wave. Right? That is the only way to maintain the same. So you do that, your sound system that has two Black Widow bass bottoms. Then you're going to have a couple mid-range speakers. Then they're going to have these small jobbies, right? Now, what is sound? I don't know if I can even. Let's see if I can do this. Okay. Yeah, this will work. I'll adjust this. Zoom. So here's my sound. So if I put this on the screen, I have this flexible. So this flexes just like a speaker does. So when I get up here, and I actually have, probably going to get in trouble, I have crosshairs. So I got crosshairs. I probably can't have crosshairs in school, but I have crosshairs for this. And if I shoot, you should be able, you can feel that. I know you can feel that from there, and you can feel that, 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 right? And it's moving the papers. In fact, there's papers on here. Let's see if I can whack these off here. Yes. Okay. Now, in my other class, I had Bob sitting right there who was bald. And I said, let's pretend that Bob has 1-inch hairs on top of his head. Because in your ear that you hear, you have these hair-like follicles. So what you're doing is you're slamming those. And if I kept doing this on Matt's head, if I kept doing this continually, this gush of air that we're pushing, it's going to take his hair off. That constant bombardment of these airwaves will damage his hair or actually rip him out. That is what hearing loss is. And there is no going back. There is no freaking way to reverse this. So once you've damaged those hair sensory follicles in your eardrum, there's no going back. And I don't know, I mean, the only way to go back is to get hearing aids, right? So when that car pulls up next to you at the stop sign and the damn thing shaking and everything else, well, they're not going to be able to hear. So I have very bad ears. I've had tubes in my ears when I was a kid and stuff like that. My ears, if I go to a concert, they will hurt. High frequency sounds, they will hurt. But this is no different than a speaker or a drum head. That speaker has an electromagnet, where am I at? Has an electromagnet that it's going to, first of all, if I just put let's say if this is a speaker, I've got it mounted like this. If I have a speaker mounted like this, the cone's going to push up. It's going to suck back in, push up. I mean, that thing's going to sit there and vibrate like this, correct? So, and what that speaker is doing is pushing air. It's concentrating air into a compression region, and that is slamming into your eardrum. So that is why you can sit there and stand in front of speakers and your whole body's moving because that thing is constantly pumping air at you. Right? I mean, no different than turning your water on and off. Turning the water hose on and off, hitting you with a water hose. Well, it's hitting you with air. So you know, though, that you can vary the frequencies. Well, first of all, let's talk about this. These right here handle, I don't think it's going to work at 20. Maybe 20 to 800 hertz. Which means this speaker cone, which I can draw for you, I got to put the cone in here now. I need some electrical wires wrapped around this. I need to plug some power into that to create my electromagnet. And that electromagnet, I'm going to cheat. I had a better drawing the other hour. Your electromagnet here, this cone, the electromagnet here, the power that goes through here varies this. It's going to suck it in. It's going to spring back. Suck it in, spring back. Suck it in, spring back. When it springs back, it is concentrating the air, just like what I just shot you with. Then when it sucks back in, it creates what's called a rarefaction region where there's hardly any air, and then the cone flexes back out. When you turn the volume up, what are you doing? You're turning the suction power of this electromagnet up so that when it flexes back, you're going to have more air, right? When you turn the volume up, what are you doing? You're actually pushing more air because it's flexing back a farther distance and it's coming back out. It's no different than a drum head. If this is a drum head, if you hit it, the drum head flexes in when you hit it, and it flexes back out until it comes back to its normal, but all that drum head is doing is pushing air. So sound travels about 1,100 feet per second. You can't change it, but you can change your frequencies, and you've all changed your frequencies. So these right here are built to flex back 20 to 800. Then they can't do it anymore. They cannot vibrate and recover fast enough. They're going to sit there and just flutter. So then you got to go to some mid-range speakers. Of course, this would be your bass. This would take your lows, right? Then you'd go to your mids. Those mids maybe 800 to, depends upon the size. Oh, they might go 11,000, maybe. But there's no way this thing's going to flex back 15,000 times in a second. You got to get a smaller and smaller cone because it has to recover faster and faster and faster each second. So you get up into these highs where you're going to have 11,000 to, I don't know, 16,000. What can hear above 16,000? They say human 20 to 20,000, but as you get older, you lose this high frequency. But those dog whistles are above the human hearing. So again, the sound is going to travel the same speed, but you can vary your frequency. If you vary your frequency, you're changing the wavelength and so on. All right.